साहेबांचा ऍक्च्युली वेलकम ऍड्रेस आहे आणि आपले राजेश सरांचं शेवटी वोट ऑफ थँक्स आहे ना आणि ISSE बद्दल आणि बरोबर
पाटील सरांचं हे आहे म्हणजे इंट्रोडक्शन ऑफ स्पीकर.
ओके ओके हा रोनक चालेल.
हॅलो
रोनक सिग्नल दे ना ओके 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 स्टार्ट.
So good afternoon to all participants and dignitaries for this program. We are proud to organize this webinar. As you know that in these critical times we could not meet in person and conduct a lecture in seminar hall. That's why we make use of the technology and arrange the seminar. Today, the Indian Society of Structural Engineering, that is ISSE, Navi Mumbai Local Center, and Engineering College, that is the Walchand College of, they are jointly organizing the webinar on very important topic, which is not very popular but very interesting, which is on the subject building extreme durable structure using compression only topology, a lesson from ancient structures. And with a great pleasure, I say that to make this event successful, we have with us some towering personalities in the field of civil and structural engineering and academia. First, Dr. Mohan Balwan Dagavkar, who is a ex-municipal commissioner and city engineer of Navi Mumbai Municipal Corporation, and presently he is the chairman of Navi Mumbai Local Center of ISSE. Also, he is a present council member and past chairman of the IEI Maharashtra State Center. Second one is engineer Rajesh Laddad. He is a renowned structural engineer and he is the present honorary secretary of ISSE Navi Mumbai Local Center. Third personality is Dr. S.N. Tande. He is the head of civil engineering department of Walchand College of Engineering. And fourth one is Dr. V.S. Patil, associate professor civil engineering department, Walchand College of Engineering. Another most important personality who is our source of inspiration and just he is behind us is engineer Shantilal Jain. He is a renowned structural engineer in Mumbai, rather in India, and he is a All India President of ISSE. He was past chairman of the Institution of Engineers Maharashtra State Center. And to enlighten us on this beautiful topic of lecture, who is designing many iconic heritage structure like Golden Pagoda in Mumbai, and he is none other than Dr. Mahesh Varma. Also, we have with us our organizing committee members, Engineer R.S. Tatum, Managing Committee, IIC, Engineer Mayur, our technical support team. So on this occasion, I welcome all dignitaries and participants for this webinar. You may be very curious about this and to get enlightened about this beautiful subject. To move, I request our beloved Dr. Dagavkar, Chairman of ST.
Hello. Some problem with the voice?
Hello.
Now it is clear. Yeah, please. Kamlesh sir, now voice is clear.
Okay. So I shall start from the beginning because I.
No. Just last.
No.
You concluding. At the last, it was the bad quality of this audio.
So actually, about the eminent speaker, have you heard about?
Yes.
So now finally to go ahead with this program. Now I request Dr. Dagavkar sir to give welcome address and some brief about the.
Hello. Hello.
Yes, sir.
Good evening to all, and I welcome all the dignitaries, and especially today's uh, chief guest and oh, Dr. Mahesh Varma, who is the expert in this compression load design, and who has, as we know, that this Gorai's pagoda also designed by him. So I welcome him, that we will be enlightened by his lecture. And Dr. S.N. Tande, HOD of Civil Department, Walchand College of Engineering. Dr. V.S. Patil, Associate Professor, Walchand College of Engineering, Sangli. And Engineer Rajesh Ladda, who is our Honorary Secretary of ISSE, Navi Mumbai Center. And Mr. V.C. Kamble, who is convener and who is always enthusiastic and very supportive about all the activities what we have been doing on behalf of ISSE, Navi Mumbai Local Center, and even from Maharashtra State Center, II Belapur Local Center, and R.S. Satamji, who is the backbone of all the activities, and with his support, we have been very successfully conducting all the program. And Ronak Jain also, who is the son of Shantilalji, who is the president of ISSE, and with his initiative, we have been doing a lot of programs. And I am happy to mention here that last year ISSE Belapur center was formed, Navi Mumbai center was formed, and this is the fourth lecture we have been organizing, and second webinar in this lockdown period. So especially I welcome all the participants, the delegates, and all the structural engineers, students, and other engineers who are interested in design of structures. Generally, today's importance is that we all know that in our generation, at least, or our previous generation, or two generations back, these RCC structures were envisaged, and we have been just learning or knowing about the RCC structures. In all new inventions or design changes or amendments are done in RCC structures. Even in colleges also, from last 30, 40 years, the more emphasis is given on RCC structures, and from last 10 years now, the there is major talk about the steel structures as to save the time in construction activities. But rarely the masonry structure design and this compression loading is taught in the or practiced in day to day. If we ask any structural engineers about the masonry design, so he will have to think so many times, because it is not his routine that they are all expert in RCC and maybe now in steel structures. So, but from our childhood and from the historical this thing, or even if we visit Western countries, Europe, America, or this Africa, or in even India, we see all the forts and big palaces, mansions, and even in our Mumbai in fort area, we see huge stone buildings that Britishers has done, Taj Mahal, we can say. So all these structures are masonry structures and standing very tall and with dignified structures. And for years together, for 200, 300, 600 years, they are withstanding all weathers, furry, rain, winds, and everything. So it is always amazing by thinking at how they have done that time. Maybe the masons or the architects or engineers of that period, they must be doing with some empirical knowledge or with thumb rules. But recently in Europe and other countries, they have various codes for masonry, cement masonry, stone masonry, brick masonry. They have courts and there have been so many amendments are going on. So Dr. Mahesh Varma, who is the expert in this, so he will throw light and he will enlighten all of us about this new but very we are enthusiastic about the new learning of this stone masonry or any masonry structure. And we all know that this golden pagoda is designed by him. So we are very eager to listen Dr. Mahesh Varma, and I welcome wholeheartedly Dr. Mahesh Varma. That everyone is very eager to listen you and to he will enlighten us. So thank you very much, everyone who has given time and present here for this lecture. Thank you very much.
Thank you, Dr. Raghavkar, sir. Now to move forward, the organization which has organized this beautiful webinar is ISSE and Walchand College of Engineering. So it is my pleasure to introduce the Indian Society of Structural Engineers. The ISSE was founded on 29 January 1997 by 10 advisory trustees under leadership of great visionary and Dr. R.L. Nene. The main objectives and aims of the ISSE is to uphold the role and status of civil engineer in construction industry with an awareness of professionalism. Another aim is to connect with all civil engineers in India to strengthen our fraternity and resolve our issues. Also, it has got another aim to assist and coordinate certification policies adopted by various authorities, that is central government, state government, semi-government bodies, including municipal corporations and all other PSUs. Also, it has got aim to update members on the development of various fields in civil engineers, that is designing, computer programming, construction, rehabilitation, research, investigating, testing, and teaching also. It arranges various lectures and trainings to disseminate the knowledge to the professionals as well as the students also. It has got 5 local centers, that is Pune, Solapur, Aurangabad, Kolhapur, and Navi Mumbai. These local centers are working under ISSE headquarters. It has got student chapter, that is MS Sabu Siddhi College of Engineering, Vaikala, MIT WPU, Pune, Shamili Devi Group of Institutions, Indore, Madhya Pradesh, Vivekanand Education Societies, Polytechnic, Chembur, Mumbai. So these are colleges which are having student chapter of ISSE. It has got total membership strength of 2000 plus. At ISSE, we have started an initiative to help the civil engineering students and fresh graduate with the construction industry through ISSE Student Help Group. So ISSE appeals to all civil engineering students to join the Telegram group to get benefited from it. All details are available on our website and Telegram group. So we request all the members to come forward and contribute your time, efforts, and expertise depending upon your interest to ISSE. So with these words, to move forward, to know about another organization which is organizing this lecture is Walchand College of Engineering. So I request Dr. S.N. Tande, Head of Civil Engineering Department, to give brief about the Walchand College of Engineering. Dr. Tande, sir.
Okay, thank you, sir. Good afternoon to all. Respected Dr. M.B. Dagavkar, Chairman, ISSE Navi Mumbai, Engineer Rajesh Ladda, Honorary Secretary, Honorable Secretary, ISSE Navi Mumbai, then Dr. V.S. Patil, Associate Professor, Walchand College of Engineering, Sangli, Engineer V.C. Kamble, who is convener of this webinar. I am very happy that webinar is jointly organized by Indian Society of Structural Engineers and Walchand College of Engineering, Sangli, on building extreme durable structures using compression only topology, a lesson from ancient structures by Dr. Mahesh Varma. Now I will brief only in 2 minutes. I will not take much time. The Walchand College of Engineering, Sangli, established in 1947, is the premier and autonomous engineering institution in Maharashtra and one of the oldest in country. It is government aided institution and well known for academic quality of its UG, PG and PhD programs, which are accredited by NBA and NAC with A grade. Since 2007, the college has been enhanced towards the academic excellence by incorporating international level academic reforms in the curriculum and adopted contemporary practices like credit-based semester system, continuous assessment, and grading system, etc. Recently, it has 8 again curricula and learning systems with the active engagement of international faculty and experts. So, Walchand College of Engineering as faculty is actively engaged in research activities funded by AICT, BST, DRDO, BARC, etc. and contribute in research publications. A large number of WCA alumni are working in leadership positions in academia, government, and industry in India and abroad. So, with this short information about the institute, so I would like to wish to this webinar, and I hope the webinar will be very interesting and will be fruitful to all participants. And thank you very much. And once again, I wish you best of luck. Thank you, sir. Hello. Hello. Yeah.
Kamble sir.
Thank you, Dr. Tande. Yeah.
Thank you.
So
Thank you.
now, we will not waste any time. So I request Dr. V.S. Patil, Associate Professor of Walchand College of Engineering, to give brief introduction of today's speaker, Dr. Mahesh Varma. Dr. V.S. Patil, please.
Thank you, sir. Good afternoon to all. It gives an immense pleasure to introduce today's eminent speaker, Dr. Mahesh Varma. Dr. Mahesh Varma is a civil engineering graduate, having an experience more than 20 years as a structural engineer. His post-graduation and doctorate were done from IIT Mumbai. He did his postdoc in masonry domes from Politecnico di Milano. He is presently working as a managing director of a Nandadeep Designers and Valuers Private Limited and Own Structural Health Monitoring Private Limited. He has many research contributions published in international journals and conferences regarding unreinforced arch, vault, domes, masonry structures. Dr. Mahesh Varma is passionate about AVD constructions, possibilities to reinvent this ancient construction technology to build extreme durable structures using materials like hydraulic lime and stone. He has played key role in the design of world's largest span masonry dome, Global Pagoda at Mumbai, with a clear span of 85 meters. His company Nandadeep is registered in the Limca Book of Record for designing of this outstanding structure. He is doing many projects of new construction comprises unreinforced vault and dome roofs. He is also working in scientific restoration and structural health monitoring of AVD heritage structures. Today, Dr. Mahesh is talking on a topic building extreme durable structures using compression only topology, a lesson from ancient structures. With this introduction, I invite Dr. Mahesh for the talk. Dr. Mahesh, please. Thank you. Can you hear me? Hello.
Yes,
Can you?
yes.
Yes, sir.
Yes, sir. Yes, sir.
And can you see the screen?
Yeah.
Yes.
Okay. So, very good afternoon to everyone who present for this webinar. My sincere thanks to ISSE Mumbai and Walchand Engineering College for organizing this event. As it is already introduced that I am going to talk more about extreme durable structures. Now, what is extreme durable? So for that we must know what we are constructing like RCC and steel. What is the life of these RCC and steel structures? Typically the life of steel structures are around 30-35 years and RCC is between 50 to 70 years. And what we are going to talk about the durability of 100 years, 500 years, 1000 years, 2000 years. Is it possible? Can we construct such structures which can remain durable for so much of the time? So this is the brief outline of my discussion. We'll be discussing what is EVD because as rightly pointed that EVD is nowadays not much practiced. So I will not be surprised that many people are not aware about the terminology EVD. We'll review ancient structures. We'll see why these EVD structures are durable and why the structures constructed by us are not durable, at least in comparison to what we are talking. We'll talk about materials. I'll share some of my experience. And because this is organized by ISSE, that is Association for Structural Engineers, and the most eminent engineering college, Walchand Engineering College, so I thought it is worth to discuss about the analytical aspects. I'll avoid going much into equation, but at least it's my duty to share some analytical facts and analytical aspects of the EVD structure. So that's what I have covered in this presentation. So what is AVD? AVD is basically arches, vault and domes. I'll try to correlate it with our current practices so you can very quickly grasp it. The arches are replacement to the lintel, or lintel what we are doing is the replacement to the arches. And the roofs what we are constructing like slab beam, the walls and domes are replacement to roofs. I'm showing you two early human developments, the early human constructions. One on left hand side is flat shape construction. It's in England. I mean, archaeologists are having diversified opinion that whether it's a place of worship or it's a place of burial ground or it's some different. So, but to me, it's lintel. It's a flat lintel as a structural engineer. So the human being have constructed this 5000 years ago using flat shaped stones, heavy flat shaped stones, weighing many tons. It's one of the world's wonder because it's constructed 5000 years ago. On right hand side, you can see aqueduct construction done by Romans, which is almost like 2000 years ago. Now, why human shifted from flat shape to arches? It's because he felt or he understood that if he want to span over a larger distance, it's very difficult to handle this flat shaped stone of that span. So if he want to construct
larger span with smaller stone? The answer is arches. And see, it took almost 3000 years for human to understand this. And where we are back on left hand side. We are again constructing lintels. Maybe it's right, maybe it's wrong. Let us analyze in today's session. I tried to find the answer in nature. I believe that already as a human being we are suffering huge losses because we are standing against the nature. We are all quarantine, almost like a quarantine in home, using mask and taking so much of the care. Even this webinar is also resultant of that situation only. And the situation is probably created because we stand against the nature, not along the nature. So I tried to find my answer in the nature. I saw that any living being, if he is constructing in curvilinear shapes. Like here you can see a nest of termite. It's a beautiful domical shape with very meaningful tail at the top to balance the dome geometry. Same you can see in nest by birds. You can find few in ancient construction as well. Our ancient builders have most of the time used curvilinear shapes. Like here you are seeing Kedarnath temple, very famous temple, which has arches for the opening, not the flat shapes, which is standing for many centuries. And on right hand side you can see the construction what we are doing. I mean, now we have associations for retrofitting, we have conferences for retrofitting, we have so many books for retrofitting, so many techniques for retrofitting, so many materials for retrofitting. But I don't understand why we forget to ask ourselves the main question. Why we lead to the situation where we need retrofitting just in even not 20-30 years. Almost as soon as we complete the construction, we can see the cracks over the structure. So we start applying crack seal before paint. So why we are leading to such scenarios? And what is so special about these masonry heritage structures that those are standing for many centuries and even thousands of the year? Here I am citing few examples. I know almost all of you must have visited these important heritage sites. Gol Gumbaj, Bijapur, which is standing for 350 years. The span of 41 meter. Like I did some couple of projects where I built 20 meter span, 25 meter span of the beam, and I was happy. I was showing people. Let's see, I made 25 meter span, but somebody created 41 meter span 350 years ago. Was he having better material? Like I am using M30 for 25 meter span. Was he having M200, M500? Or whether the steel was rather than 500, Fe500, it was Fe1000, Fe2000? Probably not. In fact, not. So still, how they could manage such span? So probably it was not strength of material. Then what it was? We'll try to debug. And second example is a Khajuraho temple, which is standing for more than 1000 years. More than 1000 years. Come on, I mean, whatever we are constructing, we never talk beyond 50-70 years. I attended the conference for Mumbai Metro where they discussed for possibility of 100 years durability. And these ancient people have constructed something which is standing for more than 1,000 years. Mahabalipuram, it is on seashore. And people of Mumbai, most of the peoples are from Mumbai for this webinar. So they know how corrosive environment is for Mumbai because it is on seashore. But this Mahabalipuram is standing on seashore for more than 1,000 years. Few examples we can cite even from outside the India. Of course, there are all over the world. There are whatever old developments are there, and which have sustained are AVD masonry. Most of it. Saint Peter 42 meter, Pantheon 43.3 meter, standing for more than 2,000 years. Roman structure. Not just old structures. I'll not say that we have really stopped practicing, because I know few people who are still practicing in AVD. Like one I am citing here is a vault constructed by Aruvile. Very impressive, very impressive. Why it is impressive is that span is 10 meter. It is constructed using mud bricks, not fired bricks. Just molded mud bricks, stabilized mud bricks, and stabilized mud mortar. So obviously has very low strength. And the thickness at the root, that is at the springing point, is just 20 centimeter. And at crown it is 14 centimeter. Has no reinforcement. Now imagine if I want to construct it in RCC. The same structure, 10 meter span. What would be my design? Maybe I'll provide, I mean, you all are structural engineers, you know how we design when it comes to RCC vault or RCC dome. We'll probably provide 250 or 300 mm thickness, both face steel, 16 mm dia, 100 mm center to center. We are not sure in which direction, so probably both direction, both face. And then finally confused whether it will stand or not. But this guy has made it in mud blocks, mud mortar, with such a tiny thickness, 14 centimeter, which we cannot probably dare in RCC. Why he could do it? Again my question, was it the strength of material? Obviously not, because he used mud. But we are all the time focusing on strength of the material. I mean, our engineering start with the subject of the strength of material. So suddenly, what is this new thing came across? So we need to debug, we need to understand. Okay, so AVD is very good. We understood it's along nature, sustainable. So why we abandon? Why we are not practicing? And strange thing, why it's not in curriculum? Why we are even not learning? We are learning Kani's method, we are learning moment distribution method, which are more like a history of structural analysis. Because nobody is practicing it. Everybody is using matrix method. Still we are learning. Because we think that it is important to know the history of analysis. We want to know basics of the analysis. We want to feel that methods of the analysis. Then why we don't want to feel about AVD? Why we abandoned it from our curriculum? Is it a lack of durability? Obviously not, because we saw that these structures are standing for so many years. Is it lack of strength? Again, not, because these bridges are designed, for example, we are seeing bridges are designed for animal driven vehicles. And what we are using it for? We are using it for transportation of heavy trucks. So it's not lack of strength. Is it lack of economy? I mean, that's obvious question we always ask. I know at the end of my presentation, this question I will surely get, whether the stone masonry is economical or not. So I'll answer it that time. Is it lack of competency? Surely, because we don't have it in curriculum. We are not learning. We are focused on strength of material. And these people have constructed without any concern to the strength of material. So we don't understand it. So when it comes to audit, when it comes to retrofit, we certify that these are not stable and better demolish and construct new RCC bridge. And that's what we are doing so many years. And that is safe for us because we don't have any responsibility. When we write that it is a safe, we have responsibility that if some accident happened, our paper is there, we'll be held responsible for giving stability certificate. But for giving instability certificate, there is no risk for us. So typically that's what we are doing. Is it lack of willingness? I mean, may not be lack of willingness, but I really fail to understand. I mean, when I see people standing in front of Ellora, Ajanta, Taj Mahal, and they say, typically, I mean, may not be everyone, but typically I heard from even civil engineers, structural engineers, आज नहीं बना सकते. Come on, somebody did it in few thousand years ago, and we are saying, आज नहीं बना सकते. So we are either not willing or not competent or both. We need to introspect. Seriously, we need to introspect on this aspect. Okay, I'll get back to my AVD. That why these AVD are durable. I mean, we all understood that AVD are durable. I have shown you that there are so many structures even on seashores which are standing for 1,000 years. The question is why? We saw that it's not the strength of material. Then what is it that we need to understand? So we'll go ahead with it. On right hand side, I have shown you very simple image. Actually, my son was playing with these blocks, wooden blocks, and I suddenly realized that this is what AVD is. AVD is just about having your thrust or load path passing within the geometry of the structure. That is what you need to focus on. So to understand the masonry durability aspect, we know that the structures standing on earth which are standing for more than 1,000 years are typically built of AVD, that is arches, wall, dome. And there are three reasons for this durability. One is nature of stresses in the joint, which is always compressive. What is so great about compression? Why compressive is more durable? Why tension is not durable? Because when we design steel structures, let us say we are designing a truss, then we are more happy with the truss member in tension, not in compression. For same forces, we can provide more slender member in tension. So we want more of the tensile forces, not the compressive. Then why I want compressive forces here? Again, we'll discuss in upcoming slides. But yes, this is one major reason, the nature of stresses. Second reason is material. I mean, whatever kind of forces you are providing, if your material is sufficiently durable, then only structure can be durable. If you are going to use material which has a life expectancy of 2 years, then your structure will stand for 2 years. So secondly, your blocks, whatever you are using, should be durable enough for that extreme durability. And thirdly, use of natural hydraulic line. We'll discuss all these aspects. So let us start with compression versus tension. I hope I am sufficiently audible, just to reconfirm if my voice is cracking or there are some issues.
No,
If somebody...
perfectly all right.
Okay,
Yeah,
perfect.
perfect.
Great. So now here I have shown you two simple figures. Case 1, I'll ask you to sleep over a stone which is resting on ground. The weight of stone is few ton. I'll provide very good mattress and etc. And I'll ask you sleep peacefully. In second case, I'm giving you option that same stone I'm sticking to roof. I'm sticking it with very good adhesive, very good epoxy. I'm giving you certifications from IIT that the adhesive is sufficiently strong to hold the tensile stresses. And I'll request you to go and sleep below the stone very peacefully. Obviously, in second case, you are not comfortable. You are fearful that this stone will collapse. There are certificates, there are calculations, there are chemical properties, all studies are done, but you are not sure. You know that day or another it's going to fall. Everybody is having structural engineer inside him. Because we saw even termite is constructing very good structural profiles for the dome. So termites are also good structural engineer. We are human being. So our inner structural engineer is completely discomfortable with this tensile stresses of the forces. Not because he is not confident about the strength, but he is sure that this strength is not durable. Day or another it is going to collapse. And who knows, if I sleep below it and suddenly it collapses, I don't want to take a risk. So here it is. When we come to the structure, when we provide beams, when we provide flat lintels, we have tension. As you can see in this diagram, which shows tension and compression in the beam, bottom tension, top compression, we all know this. But what happened when this stone was fixed? That time it was strong enough. But with the time, as the time passed, the stone cracked because there is a tension. On another hand, same structure. It's a farmhouse in Tuscan where I stayed, and I saw that left hand side was a retrofitted one by our new intelligent engineers, and right hand side photo is what is originally constructed by ancient builders. They provided very thin lintel, very thin compared to what we provided today, but provided with the relieving arch. They made sure that all forces are transferring through compression. Last 250 years, this arch is standing without any cracks. Fatigue is not related with compression, it is related with tension. Whenever tension is there, we provide the steel. And then we start with problem of corrosion of steel. Then coating of steel. Then so many things. But see the intelligence of these people. They are altogether avoided tension from this structure. So let us come to the point to understand how the arch stands. I said that it is not dependent on strength of material. So let us think about some material which has zero strength. So here you are seeing the arch which is constructed with the mortar having zero strength. In other words, it is mortarless. There is no mortar provided between the blocks. So as such, mortar has zero strength. Now we'll see whether it is capable of taking load or not. You can see that this person is applying load over the arch. So it can carry finite load without any mortar. So we'll come to what Heyman has quoted. He quoted that the question of strength of masonry can be expected to hardly enter the calculations. As such, this is a very simple sentence. But what does it mean? It means that M20 or M40 is the same. It means we are not focusing on strength of material. We never considered such aspect in design of reinforced concrete or steel structure, because whenever we are doing RCC structure, whether we ask for CU analysis or not, whether we ask for workability test, etc., etc. But for cube test, certainly we are going to ask that whether you have done the cube test, whether what is the strength of the concrete. So that is our point of focus. In this structure, the topology, that is the geometrical form, is most important thing. In other words, we came up with the new terminology which should be called as strength of geometry, not the strength of material. So we'll see it further. Now how we are constructing the arches. This is left hand side. I am showing the arch which is constructed in IIT Bombay 25 years ago. Just the 25 years ago. Provided with the reinforcement. And why arches need reinforcement? That's the basic question. Because arches are basically into compression. If there is no tension, why you need reinforcement? But okay. As I said, we are always confused as a structural engineer. And we provide both phase reinforcement, both direction for such structures. I am not different. I mean, everybody is very much limited with his knowledge. When I was limited with my knowledge regarding this AVD, I was used to do it. So these people have provided reinforcement in the arches. Then obviously it's a Mumbai. The reinforcement start corroded. So they started rectofitted. Once, twice, thrice, and finally they took down this arch, demolished it, constructed again just a year ago using again higher grade of steel, higher grade of concrete. That's our understanding of AVD. On right hand side, you can see the span of 85 meters. Which is constructed 100 years ago. Still beautiful, not corroded, very beautiful. 85 meter span compared to 25 meter span. Question is it the advancement of the technology we are talking about? I will move ahead. So as I said, this compression is one reason. If you put everything into compression, you don't need steel. There is no question of corrosion. There is no question of fatigue. It can remain in its position if not disturbed by horizontal forces. Of course, you can take care of the horizontal forces as well as it's taken care in the domes. That horizontal forces also travels very nicely in a dome structure. Advanced part, so we'll stick up to the basics. So the second aspect for the durability of this structure is the material. In these ancient structures, the first typical used material is stone. What is the durability of the stone? What is the life expectancy of the basalt stone? Do you know when the basalt stone are formed? The basalt stones are formed with the formation of the earth. And these stones are going to be destroyed. Of course, everything is going to be destroyed. These stones are also going to be destroyed with the destruction of this earth. So that is the kind of durability we are talking about. Even if you see simple sandstone, limestone, the formation took million, billion years. Obviously, we have that sort of durability available for these blocks. Even mud bricks, fired mud bricks, the 5,000 years old arch is still standing in Iran. Why? Because they put everything into compression. I'll talk about the material little more when I'll be talking about the lime. So after stones, I mean for masonry you need blocks and you need mortar. Of course you can do it mortarless also, as I have shown in that arch experiment, but that need huge accuracy. I mean if you go to Hampi, the temples are built without mortar, most of the temples, or very thin mortar layers and huge stones. So if you can construct that, if you can get rid of mortar, then durability is not 100 or 500 years. Durability is million and billion years, if not retrofitted and restored by our modern engineers. Underline. But for routine tolerance, whenever we are constructing, the stone shape has some inaccuracy. So we need a filler material and we typically use some sort of mortar. Nowadays we know only one mortar, that is cement. Cement, sand, mortar. But these ancient builders used lime. Some archaeological peoples are also using lime in their restoration works. But limes are having different varieties. Every lime is not suitable for construction. The lime which is suitable for eating is not suitable for construction, and vice versa. The lime what these ancient peoples have used in the construction are hydraulic lime, which is more like a cement. Sometimes it is called as natural cement. You must have heard about Pantheon construction, that it's a natural cement. The lime which is used in the ancient construction, even in India, any temple you go, the material which is used is natural cement. It is not pure lime. It is impure lime. The lime which contained lime plus silica. Of course, some aluminum, some Fe and etc. in small quantity, but the major portion is lime and silica. That is the same content as cement. Then why there is a difference between behavior of lime and cement, or modern cement, I will say. The difference is in process. Can you tell me what is the difference between 33 grade and 53 grade of the cement? There are two differences. One is the chemical composition, that is from 33 to 53 we have increased C3S and reduced obviously C2S. And secondly, burning temperature in kiln. We are going little higher temperature, so that C3S formation is enhanced, should be encouraged. Why we want more C3S? What is this C3S? What is this C2S? C2S is more responsible for providing long-term strength. I think I am falling short of the time, 5:30. What is my target time to complete the presentation?
Please,
Sorry, I could not hear you. Can you repeat what is target time so I can try to wrap up in that time only?
Another half an hour, sir.
Another half hour? It's good enough time for me. Thanks a lot.
Yeah.
Okay.
Yeah.
Okay. So C2S gives us long-term strength and C3S gives us early strength. And when we check the cement strength, it is at 28 days. We don't have any concern about 3 months, 6 months, 9 months, 2 years, 5 years. We are too much focused on 28 days. Sometimes I get puzzled that who invented this number 28? Why it is 28, not 30? At least a month. Maybe it must be a February or something like that when somebody must have said that test it after 1 month. But whatever the reason, we are testing it at 28 days. And we consider that to be a datum strength. Now this cement company have focused on it. They are giving us, rather than higher strength cement, they are providing us early strength cement by increasing C3S. And that's only the difference between natural cement and artificial cement. In natural cement, there is practically 0% of C3S. So the strength gaining cycle is slower. Now you will ask, what is the benefit of slow strength gaining cycle? I want to have early strength. Why I will wait for the strength development? The nature is very simple. Somebody's mic is on. I am getting disturbances. Can you? Okay, thank you. So if sun is taking 6 hours from sunrise to noon, then another 6 hours it will be sunset. That's the nature. You ask early noon, you want noon after 1 hour from sunrise, the sunset will be in another 1 hour. So as shown in the graph on right hand side, the modern cement gains early strength, loses early strength, the early deterioration. For hydraulic lime, it is slow gaining of strength. So obviously the deterioration starts after you get the peak strength. So the deterioration cycle is also very long. That is one benefit from durability point of view. But there is another two benefits, very important benefits, which I will show you in left diagram. When the lime is burned, it releases CO2. Then when you slake it, H2O is get added, you will get CaOH. Then when water is get added, it releases again, it absorbs the CO2. So CaO to CaCO3 again. That's the lime cycle. So it keeps absorbing CO2 for many hundred years, as long as the setting continues. The resultant is the carbon dioxide content of your structure is very low. You can feel it when you go in temples which are constructed of stone and lime. Compare the feeling with the temple which is built in RCC or steel. You can feel the difference. The feeling of tranquility is completely different. The reason is lower CO2 content in that temple. That is first thing. And why don't we want it in our residence? Secondly, as you can see, when lime sets, it releases H2O. And H2O is required for silica part, for setting, because it's a natural cement. So the water which is required for a curing of mortar is readily available, released by lime. In turn, it works as a self-healing material. So when the construction is finished, if you observe some minor cracks, in 3 months you will observe that cracks are vanished. I observed it on my sites many a times, practically. These are some photographs. Left hand side you can see the calcination in our lab. We have very small lab in our office where we keep doing some experiments about lime and other materials. Right hand side you can see a kiln which we constructed on our one of the site, that is near Nasik, for the construction of library building. And backside you can see, I'll just start pointer. So here you can see the stacked hydraulic lime. I repeat, hydraulic lime and pure lime are two different things. The lime which is commercially available is a pure lime. It has no silica, so no formation of CS bond. It's not durable. It will dissolve in water. But whereas if you use hydraulic lime, hydraulic means one which can set under water. That is hydraulic. So if you can get lime which has a impurity of silica, you can use it for construction. And the strength also you can get very significant. Like for 30 days strength, I will not focus on much, but 90 days strength with lime we are getting above M50 for mortar. So that's a significant strength what we are able to achieve on our sites and in our lab. This is slaking of the lime. This is molding of the lime. This becomes sticky. Once you do molding, the lime becomes very sticky, and that allows us to construct the roofs without centering. I'll show you in one video. Very interesting one. And as I have said you, the people are using lime. It's more like वो हिंदी में बोलते हैं ना चूना लगाना, तो चूना लगाने जैसी बात है. If you are using lime just because it has a name of lime, what happened I'll show you. So here in video you can see that my engineer is showing you strength of the lime which we are using on our sites, and the strength of lime from archaeological sites. Very brittle because they are using pure lime. They don't understand the difference between pure lime and hydraulic lime. Then he is comparing the lime again from our site. Very strong with the lime of ancient construction. Similar strength because binders are similar. Just not about strength but also about porosity and etc. This is archaeological mortar. You can see how porous it is. And on right hand side you can see the mortar from our site, not at all porous. We are trying our bit to do a lot of experiments which we are able to do because we are not aided organization for research. We don't have any funding for research. We raise our funding from our project and try to do whatever best we can do. Of course, there is strong support from institutes like IIT, Technical University of Milan, and other universities which are working with us, or Aruvile Earth Institute, for example. They are also working in collaboration with us for many projects. So yes, we are trying to do our best, but I know it's just the beginning. We are at basic stage. There is a lot to do, and probably the institutes like Walchand Institute can certainly take it ahead and should take it ahead. I'll show you some of my real life projects so that you can get more feel of EVD construction, how these are done, what are typicality of these constructions. One is of course Global Pagoda, which was very kindly mentioned in the introduction also. Yes, it's very massive structure. The structure which has a height of 90 meters. So when I talk about EVD with the people typically ask me how much floors we can go. So this structure is like 30-story high, which I have designed, not constructed. So, but it's already constructed at Gorai, Mumbai. It's in existence, and the clear span is 85 meters. 85-meter clear span. RCC beams you will not provide. PT you will not provide. Steel structures probably PV companies will run away. That we constructed using stone and lime. Here you can see a cross section of that global pagoda. As I have mentioned that the span of this structure is 85 meter, the height is 90 meter, and it's dome over dome construction, unique profile. Nowhere in the world you will find such dome over dome bolt construction. Here you can see some of the photographs under construction. Left hand side, first photo, you can see the span 85 meter. The cranes are looking very small in front of those spans. It is constructed without any centering. So you can just see in second photograph just the scaffolding and more like a cantilever picture, but it's not cantilever. Every ring becomes stable once it is completed. The third photographs you can see the 10,000 people accommodated in single hall under single roof. And here you can see real carvings of this stone from the same side. You can get feel of it. The next photo you can see the discussion going on about the construction of upper domes, that how to construct it, how to handle the stone, how to put the stone at such a height of 90 meter, and we were discussing about can we put the cranes. So RS Jangir was proof consultant for this project. He asked me, he's more like a guide to me, mentor to me. So he said, Mahesh, why don't you try putting a load on your first dome and check how much load you can put. So the crane load was so insignificant, and you can see really the cranes are put over the first dome, moving over the first dome and working with so many stones, and we constructed second and third dome. The analytical aspect we'll discuss a bit later at the last part of the slide or the presentation. So here you can see that this structure, and so my organization is already recorded under Limca Book of Record for design of this structure. We all should be proud because it's in India. I mean, Pantheon has a span of 43 meter. We constructed it with the span of 85 meter. So 4 Pantheon can be hosted in this single structure. The area is 4 times. So you can host 4 Pantheon, the largest stone masonry dome before this. Such 4 domes can be hosted in single structure. It is certified by IIT Bombay for earthquake resistivity and design parameters. Now, another interesting structure we are doing at Vani, that is at Nasik. It's for a library building. Again, stone and lime. Here you can see it's under construction. The 4 columns are constructed, and we are in a process of constructing of arches. Some allied structure. Also, you can see that we have constructed the arch staircase. Here you can see in photographs the checking of the centering, because shape control is, as I said, it's a strength of, not strength of material. It's a strength of geometry. So when you are talking about strength of geometry, you should be very particular that your geometry is perfect. And your geometry can be perfect only when your preparation is perfect, when your centering is perfect, when your method of construction is perfect. So we always keep doing a lot of discussion about how we are going to construct this profile. What is our methodology? We work with the contractor to decide and finalize the methodology for constructing of the geometry, and I'll tell you, it's not very difficult. It's very easy once you start understanding it. The methods are very simple. If some mason can construct a straight wall, he can very well construct the arch, he can construct the vault, he can construct the dome. On that same site, we have constructed this kiln, we have pulverizer. So it's more like we have cement plant or lime plant. because the hydraulic lime is not commercially available. So we are bent to manufacture it for our purpose and then use it. We are doing some projects for government of Maharashtra as well. Here, as you can see, for Chikaldara, we are doing guest house building. I'm doing some residential project also. I mean, you will say, what's so great in residential project? It's a small project. But there is a lot to learn in these small projects. I will show you rampart, I will show you vault, I will show you vault construction, and you will be amazed by the way it is constructed. And think about, you have a house with lower carbon dioxide content, more livable, more aligned with nature, more durable. What else is required? So here is a video for vault construction. It's very interesting how we are constructing the vault without any centering, using hydraulic lime and red bricks. So here you can see mason who is constructing. As I said, it's not difficult. The mason who can construct straight wall can construct curvilinear curves, vaults and arches. And typically, I always use local masons. I do not use special masons. I should not take credit. My wife take lead into training and site execution. She takes more on training part, and we train the masons for construction. And as you can see, the mason is putting brick after brick, sticking it. As I said, the lime mortar is very sticky. The brick can very easily stick to the previous brick. You keep constructing, require no support. Just the central point, he is putting a thread to check whether the joints are radial or not. Putting another brick, and that's it. And you can see some hanging bricks here. You can see this hanging bricks. Maybe if somebody is interested, we'll discuss about it, why those are hanging. Okay, so I'll move ahead. Maybe. Yeah, so here you can see the vault which is under construction, then another stage towards completion, arches after arches and closure. And this is the left hand side is a completed house with this beautiful vault. I must point it out. The rampart arch. So staircase is also not RCC, that is used using compression profile. Arches not lintels, walls not slab, no RCC, brick load bearing walls. And right hand side you can see rampart photo under construction. This rampart is very interesting profile. I must admit at this point that I am at very primitive stage to understand this technology, because if you see this photograph, this is a rampart arch which is constructed by ancient builders. It's at castle at Rome. I've forgotten the name of that castle. Okay, so there I saw this rampart arch with almost flat profile. I am still to dare it. I analyze it and I found that, my God, with such a small rise, it's possible. I can construct it. But the level of accuracy, probably I need to work really hard, or maybe somebody else will work so hard, and maybe one day human being will be capable to construct such profiles. I hope so. But typically rampart is an arch which is flying from one level to another level, which can be used for staircase. It can be catenary, it can be parabolic, it can be circular, or many possible shapes. Most of the time we use segmental. We typically design firstly catenary and we try to fix up the segmental shapes which matches with the catenary shape, because these segmental shapes are easy to construct. It's bit of the mathematical formulation, but I don't want to go, and time also does not permit me to go into more deeper into it. So I'll just run over it. But basically you need common tangent points for different segments of the rampart arch. And of course you must be sure that thrust is passing within a geometry of the structure. This is the drawing. This is how we give the detailing of radius, center, if center is available. If center is not available, then we have to give, because we have to work with the contractor to assist him that how he is going to draw that profile. We also did arch foundations in our project, very successfully implemented. We have also done conical vault with Aruvile Earth Institute. I mean, they are the main designer of it, and we have supported with the analysis. But very interesting, you can see that the arch construction, the thickness of the vault, its arch is so small, less than 2 inches, and the span is 15 meter. What a level of accuracy they are maintaining! Fantastic. And very beautiful. It is published by MIT USA in their international journal as an amazing structure. Span is not large, 15 meter is not large, but the way it is constructed, it's very beautiful to see. We are also doing some other projects for government of Maharashtra, like Krishneshwar temple development, Sabha Mandap, Bhakta Niwas, etc. We are also doing some retrofitting project, like here you can see Kasara stone masonry bridge. But I'll make a point here. I mean, see, these structures are priceless. What is cost of this bridge, stone masonry bridge? Or what is the cost of Taj Mahal? Probably 1,000 crore, 10,000 crore, lakhs crore. I don't know. Nobody can valuate it. Valuation is impossible. So when we are dealing with such structure, I sincerely request that we should try constructing some arches on our own. We should try it, we should learn it, and then only we should disturb this structure. I strongly believe that the way we are doing retrofitting of the masonry structures, we are deteriorating them early rather than retrofitting it. Anyway, I'll not stress much on this point. But we did a methodological analysis, we did structural health monitoring, like Hone Structural Health Monitoring India Private Limited. My another company works in structural health monitoring. So we put a lot of equipments to check the growth of crack, change in crack width with temperature, with humidity, with movement, everything to establish our to check our mathematical model, to be sure that whatever analysis we are doing, we are understanding the behavior of the arch, and we are not demolishing the arch bridge just because of single crack. And finally we come out with the retrofitting schema for that particular arch bridge, which is under implementation now. We also do workshop for teaching the vault construction, arch construction. Very quickly we'll go to the analysis of EVD structure. We are finished with the time. So very quickly, another just overview we'll take. Analysis of EVD structures. Here I have cited one very good statement from Alchemist. The statement says that we typically complicate the things. We love to see the things in complicated way rather than simplified way. And probably when finally we understand everything, we will understand that the things were very simple and very basics. And that is true about the EVD structure analysis. I really want to emphasize this because I see many structural engineers who complicate it like hell when it comes to the masonry analysis, and very ineffective, inappropriate use of the finite element models. That's what I many a times see. So just the alert for young engineers that when you are using tools like finite element, you should be very cautious. Basically, it's a geometrical analysis. It's not the strength of material analysis. It's based on basic assumptions. Like here I have mentioned, masonry has no tensile strength, infinite compressive strength, and sliding failure cannot occur. So these are the basic assumptions to simplify the analysis, and these are valid assumptions. Hemans have given a detailed explanation why these assumptions are valid and how due to these assumptions strength of material goes outside the picture. So somebody can refer to his paper rather than I to discuss much about it. As I said, finite element is most misused method for the analysis of masonry structures. Why misused? Because what kind of analysis result we are getting? We are getting stresses, we are getting strengths. But I already mentioned that stresses are not important because strength is not important. So the output what we are going to get is not at all useful for us. Moreover, it's impossible to do interpretation of the mechanical properties of the material. I am citing just two eminent researchers here. Like one Hotra, he is saying finite element analysis can add only noise to masonry analysis. From ETH Zurich, Philippe Bloch is saying that FEA analysis cannot effectively be used for masonry analysis. Basically, ancient builders use the geometrical analysis, which is like thrust line analysis. The benefit is it's very easy to understand. The difficulty is cannot be analyzed the complex structural behavior. On another hand, if you see finite element analysis, the benefit is you can analyze any complex geometry, but the result are stress strain. So what's the use of those results? So we come out with the completely new analytical approach, which is called as fate law. Nowadays used by many universities, many engineers. It's a finite element thrust line analysis, which combine the geometrical analysis with the finite element analysis. So I'll stick to the time schedule and I'll not go ahead with my presentation, but maybe in some other presentation we can discuss more about the structural analysis part of it. I'll move ahead. It's very interesting how the masonry can be analyzed. There are many publications which are published by me on analytical aspects of the masonry structures. Here the references are given. Interested audience who really want to go in more detail of the structural analysis part could refer to these references and get back to me on their doubts. My last question to everyone: can we create heritage? Come on, if somebody has created heritage 1000 and 2000 years ago, one who, if come to our world, will be amazed to see that we are going on moon, we are going on a Mars, we are flying, we are running with so much of the speed, we are so developed, and we are saying that we cannot construct the structure which can stand for 1000 and 2000 years. Is it really our limitation? We always say that we are proud of heritage which are given by our forefathers, but what is it that we are going to give to our grandchildren? What they will be proud of on our generation? Secondly, can we compare the peace of mind which we can get in these structures, EVD structure built using lime, with the RCC and steel structures? We need to think that whether all our structures are going to be replaced before us. Like Mumbai, we are constructing so many structures 35 and 50 years, if we stop constructing, you'll again see only old buildings, no new building. That's the kind of structures we are building. My sincere thanks to all those who are present, and my most sincere thanks to my team, Nandadeep team, Home Structural Health Monitoring team, who are real working people and allowing me to present on their behalf and take the credit of the work which they have done. So thanks to them, thanks to you all for so patient and to listen to my presentation. Thank you. Handed over back to you, sir.
Thank you, sir. Thank you very much, Dr. Varma, sir, for delivering such eye-opening lecture, which enlighten us about the ancient technology, but now mostly, most probably, we are expecting you to resume mechanical durable structures. You have explained nicely in a simple manner with lot of illustration, which had really penetrated in our mind and will remain for long period like a durable structure. So thank you very much. And now coming towards the last part of the program. So before that, we request all these participants, if they got any doubts in their mind, the time is, we have provided around 10 minutes for that, for question and answer. If anybody has got any questions, any doubts, they put their doubts in this chat box. And sir, you can see the chat box and answer the questions. Ronak? Hello? Yeah, yes. Dr. Varma, please.
Okay. So, as I was expecting in the beginning of my presentation that there... Hello? Yeah. So the first question which I was expecting is about the cost. How much cost saving we can do. So I'll explain it in little different manner. Like we do AVD and we do RCC. In RCC we use concrete, and in concrete we have three ingredients: cement, sand, and aggregate. Which is strongest of it? It's not cement, it's aggregate. Stone aggregate is the strongest material. Which is cheapest? Again, stone aggregate is the cheapest. So in concrete, the cheapest ingredient is a stone. So ideally, our stone masonry should be a cheapest one compared to the concrete. But the problem is we are not practicing it. The thing is we are not practicing it, so the machineries are not developed for carving of the stone, for dressing of the stones. So the cost is very high. Industrialization is not supporting this technology yet. So the cost is high. So to come to the direct answer, I'll say the presently it costs, like if I go with a brick and lime, the cost is 1.5 times the cost of the regular construction. And if I go with the stone masonry, the cost is 3 times. But I strongly want to say that if it is practiced, there is no reason that this should be more costlier than regular house. It should be much cheaper and it should be cost effective technology. Sir, next question, please. Okay, second question is how to prepare lime and surkhi mortar. So see, as I said, lime need to be processed. You get a limestone. Limestone need to be put into kiln for processing. Can you see still my slides?
Yeah.
Yeah, so here as you can see, lime is put into kiln. So CO2 is released, it becomes CaO. You add water, it becomes CaOH. You do mulling, it becomes very sticky, it start absorbing CO2 from atmosphere, it becomes sticky as shown here, very sticky mortar, and then you can use that with surkhi. Now surkhi is a silica, so silica part get added more into it, the cost get reduced. It's a pozzolanic material, so you need to do mulling. Typically mechanical mullers you can use for mulling of this mortar till it becomes sticky. That's how it is prepared. Next question, please, sir. Okay, can we think of structures like Burj Khalifa having no tension and flexure? So that's an interesting question. As I would like to put, like I did 85-meter span. That time the same question was asked by a client. My father N.R. Varma was leading our team. So that time Subhaji asked this question. Is it possible that we can construct 85-meter span in stone? Because nobody have ever constructed it. The maximum span is 43 meter. So are we sure? That time my father answered, we are not sure. But if the same question is asked when Wright brothers invented the flying machines, which we call aeroplane, then probably we would not be flying today. So we need to believe, we need to study, we need to be utmost sincere with our efforts, and then we need to try. I strongly believe that when I can construct 85-meter span, I can construct 300-meter span as well. The Burj Khalifa may have some different topology, which may not be suitable for compressive structure. But with compressive structure, you can create magnificent, super strong, large span, heighted structures. Everything is possible. So yes, the possibilities are immense. The idea is basic. So I'll go to the next question. How we can ascertain the strength of AVD structure? We can be ascertain of the strength of AVD structure by visiting Taj Mahal, by visiting Ellora, by visiting Ajanta, by visiting any ancient structures, by going to Kedarnath temple which survived when none of the RCC structures survived. We may not be certain about our capabilities, we may not be certain about our willingness, but there is no reason to blame AVD technology. There is no reason to blame this particular methodology. In fact, I'll share you one small example discussion when I was doing it for Government of Maharashtra. One of the engineer who was representing PWD told me that these arches are not earthquake proof. I said, sir, the Taj Mahal is under you for restoration. Why don't we replace all arches with the lintels? Come on, this is blunder statement to say that arches are not earthquake resisting. These structures are standing for so many centuries. These structures face the earthquake. So what other proof we require? So I'll go to another question. Are there any other application of rampart arch except staircase? Yes, flying buttress. The beautiful flying buttress. Go to Europe, not right now, it's not good time to visit Europe. But after this, maybe after a year or so, visit Europe and see beautiful flying buttresses to the churches. And those are rampart. Lastly, how to overcome hoop stresses in arch structure. There is no hoop stresses in arch structure. There is a hoop stresses in dome structure, and it's a big trouble. It's a big trouble to many ancient structures, like to Pantheon there are cracks, to Saint Peter's there are cracks, to Gol Gumbaj there are cracks. So there are cracks. But the question is, should we overcome, or can we live with those cracks? Probably second is more right. You can live with those cracks, or while construction you can plan to avoid those cracks. Yes, it is possible to have hoop tension less geometry. Just quickly, yeah, you can see these hoop cracks which I am showing. These are all hoop stresses crack, and my analytical tool which I have developed is capable to handle this hoop tension, can release the hoop tension, do iterative analysis and plot the thrust line, and to give the stability after the cracking without knowing the modulus of elasticity and other properties. It's a bit interesting. You can go and read my publication. The next question here I can see is how testing of AVD is done. Testing is, if you know how it can fail, you know how to test it. For example, here you can see testing which we conducted in collaboration with Arvile Earth Institute. For like we analyze the dome, we calculate the actual load which it can sustain. Very thin vault, just the 2-inch thick vault dome. We constructed it with most accuracy, and we added the load using sandbag. The sandbag, empty sandbag was put over it, and slowly with known rate of the loading, we have poured the sand into it. And we saw that up to what load it sustained. And with slow speed camera, we have captured the failure, that which crack appear when, from where the crack starts, and etc. These are all experiment. And probably the academical institutes are more capable to do the experiment. For me, I mean, I am not the researcher. I am the practical person who is willing to construct, demonstrate, and give to society usable structure. But because nobody else is doing research, I am forced to do research in this direction. But I'll do my best to identify the opportunity with this technology and to give whatever push I can provide. Thanks.
Can we specify different books to analyze this type of structure?
Is there any other question? Let me see. I think question answer also we are okay. Is this all questions? Okay, thank you. Back to you, sir.
Okay. So actually the question and answer I conclude here. And now if anybody got any doubts, then they can have our this mail ID on the invitation. So they can send their queries or any doubts on that. And we will pass on to Dr. Mahesh sir, and will reply you as soon as it comes to us. So thank you very much. Now I request our Honorary Secretary Rajesh Ladda sir to cast vote of thanks, please.
Good evening, everybody. It gives me immense pleasure to do the honors, the vote of thanks, and I thank you, Dr. Mahesh Varma, for sharing his valuable knowledge and experience and giving us food for thought to explore such beautiful construction system, which I don't know is lost somewhere. We need to reinvent ourselves, and I think it is only R&D which helps us to reinvent ourselves, and this is the time where everybody has got extra time to reinvent themselves, and there are people like Dr. Mahesh Varma who can help us out in understanding this subject, and I thank you very much for sharing your valuable knowledge, sir, and I hope you all the best in your life and future endeavors. And thank you everybody for joining the seminar and giving us your valuable time and making it a success. Thank you very much. Over to you, Kamesh sir.
Okay. So we conclude here. and the session is over now. Ronak, please close that